All right, so in this video, we're going to look at the growing dots task. And the first thing that I did here, and the first thing that we're going to think about is how we see this figure growing. So at first I have these 3 dots, and then I see my new dots next to them. You could see them on the other side. I see my new dots next on top. And I see 1 new dot in this time at each of my 3 corners. Now I see 2 dots in each of my 3 corners. Now I see 4 dots that are new in each of my 3 corners, and now 8 dots. So one way that I would describe this is each of my corners are doubling. So I'm having twice as many dots as I did before. So here I had 2 dots. Now here I have 4 dots. So the 2 dots that I had doubled. Now I have 2 rows of 2 dots. Over here I have 4. So I have a group of 4 and a group of 4. So I have my 4s that doubled. Now this is 8. So now I have 8 and 8. So it's just a way of explaining how you would potentially see this shape grow, or these shapes growing at the beginning, 1 minute, 2 minutes, 3 minutes, and so on. So we're going to start working on this growing dots task. And the first thing I want to figure out is who's going to be independent and who's going to be dependent. So do the number of dots change based on what minute we're at? Or does the minute that we're at change based on the number of dots? Well, the time that's going by is the independent, and the number of dots depends on where we are in time. So I'm going to start making a table. And this is very similar to the growing dots task we did in Unit 2 when we started learning about arithmetic sequences. So looking at your picture, we can fill in at 0 minutes, we had 3 dots. At 1 minute, we had 6. 2, 12. 3, 24. And 4, we had 48. Now, what we did in our previous unit is I looked at how to get from 3 to 6 and from 6 to 12 and from 12 to 24 and so on using addition. Well, if I did that with addition, this would be plus 3, this would be plus 6, plus 12, and plus 24. It's not the same number with addition. That tells me that addition is not the correct way for me to move through these output values in my table. I have to come up with something different. If you listened to how I was saying before, I saw that these dots doubled. That's actually what's happening here. If I double 3, I get 6. If I double 6, I get 12. If I double 12, I get 24. If I double 24, I get 48. So my pattern here is times 2. Now I'm not looking at addition anymore. So if I wanted to get number 5, I would double 48. So 48 times 2 gives us 96. So this times 2 before, when we were dealing with an arithmetic sequence, we called that a common difference. Difference denoting that we were doing addition or subtraction. Now, this is called a common ratio. And since I'm dealing with multiplication, instead of addition or subtraction, we're no longer dealing with an arithmetic sequence. Now, we're dealing with a geometric sequence. So arithmetic goes with a common difference that has addition or subtraction. Geometric sequences are dealing with a common ratio that is multiplication. So just like we did with growing dots, we're going to look at this with sequence notation. And I'm going to kind of make a mega table here, as I like to call it. I'm going to show my work. And then I'm going to rewrite it over here. And I'm going to simplify my work. So I'm going to copy these down here. 3, 6, 12, 24, 48, and 96. So there's no real work I'm doing here. It's just 3. To get to 6, I had to do 3 times 2. To get to 12, I had to do 3 times 2 times another 2. And this should start looking very familiar to what we did with growing dots. So here I had to multiply by 2 3 times. To get to 48, I had to take what I had before and multiply by 2 again. So this is just 3. This is 3 times 2. This is 3 times 2, and there's 2 of them, so it's squared. This would be 3 times 2, and there's 3 of them, so that would be cubed. Here it would be 2 to the 4th, and if I wanted to keep going, this would be 2 to the 5th. Technically, this is 2 to the 1st. And if I went back here, this would be 2 to the power of 0, which remember from our exponent rules is 1. So this would be 3 times 1. This would be 3 times 2. This would be 3 times 2 squared, which is 4. So now our goal is going to be to write an explicit formula. And I'm going to move this up here out of the way. And remember, since it's a sequence, we use A sub n and n as our input and our output. So one thing I notice is every single time I'm dealing with 3, another thing I notice is I'm doing times 2. But what I need to figure out is how these changing exponents relate back to where I was at the beginning with n. And each of these exponents are identical, so my exponent is just n. So this is my initial value. This times 2 is my common ratio. And we're going to talk about how our exponents relate in an example I'm going to do with you in just a minute. But remember, it's always my initial value and my common ratio, just like it was with an arithmetic sequence. And just like it was with an arithmetic sequence, we have a recursive formula. And that's always a sub n and a sub n minus 1. The only difference is since it's multiplication, normally we see that out front. So this would be our recursive, and this would be our explicit. So the other example I'm going to do with you, I'm actually going to do 2 more examples with you. So let's say that I have the same output values of 3, 6, 12, 24, and 48. But instead of n starting at 0, I'm going to have n start at 1. Well, this is still 3, and this is still 3 times 2, and this is still 3 times 2 times 2. So the simplified column here is still going to have the same numbers. So 24 over here, we had 3 times 3 2s, so 3 times 2 cubed. That's still the same. And this is still 3 times 2 to the 4th. And this is still 3 times 2 to the power of 0 and 1. So that part has not changed. Now what I need to do is figure out how to relate this exponent to my new n values. Well, how would I get from 1 to 0? How would I get from 2 to 1? How would I get from 3 to 2 and 4 to 3 and 5 to 4? It's 1 less. So in this case, I'm still dealing with explicit. I still have a sub n, and I still have 3 times 2. But now for my exponent, it's not going to be just n. It's going to be n minus 1, because these are all 1 less than the n value. That n minus 1 should look very familiar, because that's what we dealt with the entire part of my arithmetic sequence unit for 2a. So this is our initial value. And I'm going to specifically say output. 2 is my common ratio. And then the minus 1 here is my first input value. So if I had started with n equals 3, well, then I would be doing n minus 3 in my exponent instead. And the only way I'm going to tweak this and make one more example is I'm going to keep the same output values, but I'm going to invert them. So instead of starting with 3, I'm going to start with 48. So this would be 1, 2, 3, 4, and 5. And this is going to be 48, 24, 12, 6, and 3. So before here, my pattern was times 2. Well, now I'm going the opposite direction. And normally, our brains would think divide by 2, which is totally valid. And yes, it is correct that we are dividing by 2. However, when I'm dealing with a geometric sequence or an exponential function, this is always written as a fraction. If you don't know the fraction off of the top of your head, you can always do the second output divided by the first output. And that will tell you what fraction you are multiplying by, which in this case is just 1/2. So I'm going to build my explicit formula. So I have my initial output value, which is 48. Now, since this is a fraction, I tend to use parentheses. And honestly, you could use parentheses up here around your common ratio. Typically, you will see your common ratio in parentheses. And then n minus my first input, which was 1. So my first output, my common ratio, and my first input. And that will always be the case with these geometric sequences. Now, if we were going to look at this on a graph, I'm going to go back just to our original. Let's see if I can find my original table. So here's my original table. Now, if I graphed this, you'll notice I am counting by sixes. I don't know why I started with blue pen and then picked up a black pen. Whatever. So this would be 36. So starting to graph this, let's see, I need to keep going a little bit. This would be 42 and then 48. And then I'm not gonna keep going all the way up to 96. That's just too much. All right. So times 0 is at 3 dots. Times 1 is at 6. Times 2 is at 12. Times 3 is at 24. Times 4 is at 48. All right. Now, yes, my Y scale, I counted by sixes just so I could get it into this picture. Since this is a sequence, I'm not going to connect the dots because remember, there's nothing happening in between each time value of each minute. But what you will notice is now I'm no longer dealing with a straight line. Now I'm dealing with a curve. I could still see the change. And let me do this in a different color. So here, I'm going over 1 minute, but now I've gone up 24 dots. Here I'm going over 1 minute, and I'm going up 12 dots. Here we went up 6, and here we went up 3. So I can still see that pattern. The amount that I'm increasing is doubling. So you can still see, even if you're using dots and this curve, you can still see how our graph is changing. But the most important thing to realize now is I'm not dealing with a linear function anymore because we have now moved to this pattern of multiplication as that pattern as how we're changing our table.